Good morning. Happy Friday. So, I would like to introduce Dr. Peg Smith from the University of Pittsburgh. She is going to be talking this morning about the 5 practices and how they relate to math. And she has a new book coming out, which is not out yet, that will be related to the 5 practices in science education. So, that's awesome.
Well, good morning, and thank you all for coming. Before I get started, let me just ask a question. How many would identify themselves as a science person? Be bold. Okay, a couple, good. And I'm assuming the rest of you would call yourselves math people of various stripes. Okay. So I'm going to talk a little bit about orchestrating productive discussions in math and science. How many of you have seen that little book before? Okay. So some colleagues of, this is a book that I co-authored with Mary Kay Stein, but the set of ideas that are talked about in the book actually come from some earlier work that I did with Mary Kay Stein, Randy Engel, and Elizabeth Hughes as we were starting to sort of figure out what these practices were. And it resulted in this book, which was intended for a practitioner audience. We've written pieces that were intended for different audiences along the way. And one of my colleagues at the University of Pittsburgh, Jennifer Cartier, who is the director of teacher education at really, and a science educator, I should say, really thought the ideas here spoke to her as a science educator. And she started using the book with her science students. And so one day, not all that long ago, maybe last fall, she came to me and she said, you know, I think the ideas that you talked about in this book really speak to science as well as mathematics, and it would just be really nice if we had a science version of the book. And I think we need 5 practices in science. And I said, yeah, well, I would not be the person who should be tasked with that particular chore. And she said, well, I could help you. And I thought, well, it's going to take a lot of help. But lo and behold, the Green 5 book, the blue and green book, is the 5 practices in science, which will be published in October, co-published in October by NCTM and NSTA. And this is a first for NCTM to publish a non-math book. So getting the support from NSTA was really important in this. Jennifer is the first author of this book for a very good reason. I credit her with anything that's sensible in it about science. That's not to say, I don't want to sound like one of those people say, I can't do math. I can do science, but I don't feel as though I'm an expert in science, and she is, and anything that is bad in that, you can blame me, and anything that's good in it, you can credit her. At the end, I'm actually going to give you her email, so if you have particular science issues you want to raise, you can tell her. I told her I was going to do that, so she's prepared. Anyway, so I'm going to talk about the 5 practices somewhat generically so that it would cross math and science, but when we start talking about tasks, I am going to give you some particular examples from science because I have become convinced that science tasks and math tasks are quite different in what you mean by task. Okay, so what's standing between you and lunch is basically these 3 bullets. I'm going to talk about the importance and challenge of facilitating discussions in math and science classrooms. I'm going to talk about the 5 plus practices that teachers can learn, and we'll talk about the plus as we go through this. How the 5 practices could help improve teaching, and then hopefully I'll have a little time to talk about some research efforts that we've been engaging in to try to understand what teachers can learn about the 5 practices and how they apply them to their own teaching, and what might be some of the difficulties associated with doing that. And so let's just dive right in. So I think that in both disciplines we've come to believe that discussions are important things to engage students in. They allow students to share ideas and clarify understandings, develop convincing arguments, which is standard for mathematical practice in the Common Core. It's also one of the practice standards in the next generation science standards. Develop a language for expressing ideas, learn to see things from different perspectives, and so on. So while everybody can agree that discussions are important, they also seem to recognize how challenging they are. Namely, I see discussions as challenging because you've got to now take all these ideas, different ideas, and make sure that they all add up to something. So, I mean, I've seen lots of discussions where kids share and people talk and it's all good, except at the end of the day you leave the room and you think, what exactly was I supposed to learn about mathematics or science as a result of that? I mean, there's lots of things running around in the atmosphere, but nothing ever got quite consolidated. There was no clear, I call it storyline, that all led up to a big crescendo that was really clear. So if you think about expert facilitation, if you've ever seen something that was expertly facilitated, you probably noticed that there's this ability to diagnose student thinking on the fly, that the facilitator is able to fashion responses to guide students to evaluate each other's thinking and to promote the building of content over time. And of course, this kind of skillful improvisation requires a deep knowledge of content, of pedagogy, of students as learners, and being able to make decisions like in a split second. So when you describe it that way, you go, and how do we expect people to be able to do this? So some of the sources of challenge come from lack of familiarity. A lot of times we're asking teachers to engage in a practice which they never got to engage in when they were learners of math or science. And it reduces teachers' perceived level of control. So as soon as you are trying to build a discussion around the thinking of somebody other than you, then you automatically have relinquished some of the control and some of the authority for what happens next to the students in the classroom, which is a pretty scary proposition when you're thinking about turning over things to a 12 to 17-year-old. It requires complex split-second decision, requires flexible and interconnected use of knowledge. So, okay, it's important, it's challenging, so what? So this is where we thought the 5 practices can come in. So the goal of the 5 practices is to make student-centered instruction more manageable by moderating the degree of improvisation required by teachers during a discussion. So what I mean by that is that by careful planning in advance of the lesson, I'm going to argue that you can anticipate a great deal of what is likely to happen. So everything you do during the lesson isn't just improv. So one time someone said to me, math teaching is like, going to the comedy shop. I mean, you just have to roll with what happens in the moment. And while there's probably a certain amount of that, you can predict a lot of things that happen, particularly the more times you've done something, the more experience you have. But even as a beginning teacher, there are a certain number of things that you can probably count on are going to turn up in a class if you're working on a particular topic. So just to be clear about where this all comes from, a question somebody asked earlier reminded me of it. This work on the 5 practices, which is more recent, really builds on more than 20 years of work where my colleagues and I have been thinking about cognitively demanding tasks, what happens to them in the wild, and what are the reasons why tasks don't always work out the way they're intended. So some early work showed that the majority of tasks, high-level tasks, ended up being implemented in ways that reduce the cognitive demands. So one of the things that's really key here is the purpose of the 5 practices is to do this, but it's all about giving teachers a model they can use that will help them, we hope, maintain the demands of a high-level task during implementation. So this is very much related to all the stuff about tasks. So having a high-level task is certainly, to me, a necessary beginning condition. But if you can't keep it up, if you can't make sure that the task lives up to its potential during implementation, then you've really lost the benefit that's afforded by using such tasks. So what I'm going to do first is sort of run through the five plus practices and then take each one of them apart in a little bit more detail. And I'll explain the plus. Okay, so the first practice is anticipating, and this is basically the idea that prior to the lesson, you want to think through the different strategies or approaches that students might use to solve a task, both correct and incorrect, complete and incomplete. But you also want to go a step further than that. You want to actually think about what are you going to do when those things happen. So it's not enough just to say, oh, I think students are going to use an additive approach instead of a multiplicative approach. Okay, fine, good. But then what are you going to do? So you walk around and you see students who are using the additive approach. What are you going to do to help them make progress towards what your goal is of the lesson? Are you going to say, that's not right? Why don't you try it this way? Well, I might say that's not really building on students thinking so much. So trying to think about what you're going to do with this variety of things that could happen. Monitoring is the process of actually listening and watching and recording as you're walking around the room while students are working on a set of tasks. So it's not just talking to a group, although it may include that, but it's really trying to hone in on what are the strategies students are using, what are the difficulties they're having. If they're really struggling, then you want to be able to ask some questions that will help them get back on track. So some of the questions that you generated while you were anticipating are the ones you're actually going to use while you're monitoring. And this isn't about going around and doing triage or tutoring every group in the room. It's about making sure that they're moving in a productive direction and have enough scaffolding to move forward. It doesn't mean you can't leave the group until they arrive at the correct answer. The next one is selecting, and this is about determining which solutions that you would want to have presented based on the ideas that are available in the classroom. So the data that you collected during the monitoring phase would help you in determining what you would select. Sequencing is really the order in which you would put these solution strategies so that it forms a coherent storyline. And the last one is connecting, and this actually has two meanings. It's both making connections between different solution strategies that have been presented, and also making sure that you're making a connection between a particular solution and the key ideas that are at the heart of what you're trying to do in the lesson. So what's with the plus? Now, there's actually two more practices. So my students always say to me, didn't you realize that there were really 7? And yeah, I did, but not soon enough. So it was clear at some point that there were 7 things you needed to do, but I didn't really think about the need to include the first 2 as part of this list. So a couple of years ago, probably more than that, I always think something happened a couple of years ago, and then someone will say that was 10. So it could be that many. I was talking about the 5 practices with a group of coaches in Los Angeles, and one of the coaches said, you know, I think there's something missing here. And so he went on to explain that he thought that we really needed to name the practices of setting goals and selecting tasks, because to engage in anticipation without being clear about what you're trying to accomplish, and that you have a task that's aligned with the goal and it's likely to be able to help you accomplish it, there was no point in engaging in the rest of them. So I said, I thought that was a pretty strong argument. I went away from that discussion thinking, well, I had always just assumed that those would be things that you would do first. his point was that he didn't think that was a valid assumption that you should make, and if you weren't explicit about it, you're going to have people jumping into anticipating without having done the beginning work. But of course, we'd already written stuff, and we called it the 5 practices, so if you read everything up until, there are a couple of articles prior to the book, there's no mention of these 2 practices. But so when we sat down to write the book, it's like, I think we have to be really honest about what you need to do first. So I think in chapter 2, 1 or 2, maybe I always get them wrong, 1 I guess, we talk about these as a priori practices, and we also talk about them in the science book at some level of detail. And here we're just talking about being very clear about what you're going to accomplish and what you're going to use to accomplish it. So I decided to make it 0. So it was 0 through 5. I know that's a little bit, still 7. I have a colleague who's always saying that I have a counting problem. Okay, so what I'm going to do now is I'm going to go through each of these. But one of the things you might notice is I've listed a bunch of references after the 5 core practices. And the reason is I want to acknowledge the fact that it's not like any one of these things is a new idea, and nor that we want to take credit for these, because as you can see by the dates, a lot of people wrote about some of these things long before we did. But I think that what our work has brought to the table is sort of packaging these things together as a coherent model of things you can do to improve instruction. So standing on the shoulders of giants sort of thing here, if you look at the names on the list. And our contribution, I think, is the way in which we've put these things together. So the first one is setting goals. And here, it involves identifying what students know and understand about the discipline and being as specific as possible to establish a clear goal. And the thing I want to make a point here is, and I do a lot of work with teachers, both practicing and in-service teachers, and one of the things that I notice is most of the goals are written, as I would call them, performance goals. It's what you want students to do. Students will use the Pythagorean theorem to solve problems where they need to find the length of sides A, B, or C. Okay? And I'm not saying that's an unreasonable goal to have. But what I will say is I don't think stating the goal in that way is going to do as much work for you as stating it in some other way. So for example, what I want to see is, what is it that you're going to understand about mathematics as a result of what we're going to do today? So tell me what we're going to do, but then what gets left behind? As Jim Hebert would say, what's the residue that's left that's about understanding the discipline from having done whatever it is you were doing? So regarding the Pythagorean theorem, I would rather say students will recognize the relationship between the areas of the squares that are built on the legs and hypotenuse of the right triangle. Now, surely that relationship ends up being defined by the Pythagorean theorem. But understanding something about that relationship and how those areas are related would lead you to select a very different task than if all you were worried about is finding A, B, and C. So trying to be really clear about the mathematical or the science targets that you're looking for. So it's supported by thinking about what students will come to know and understand rather than just what they will do, consulting resources that might help in unpacking the ideas. The name of it escapes me, but there is a great science resource online that actually has all kinds of information about students' misconceptions in particular science domains. And there's actually some math that's in that as well. So places like that could be really helpful in trying to think about and thinking about what the goals are, what you're trying to accomplish. The books, the Essential Understandings books in math are very helpful in thinking about what are the big ideas that you want to target in the lesson. Okay, so selecting a task. So first of all, I think it's fair to say that every single thing you teach, whether it's math or science, probably doesn't warrant a whole class discussion. Some things may be better taught in some other way, and you probably literally don't have time to do a whole class discussion in every class every day. So that isn't an expectation that I have. But I think when you want to have a whole class discussion, then I'm saying that's when the 5 practices come into play. And whole class discussions ought to be about tasks that are worth talking about. I've seen lots of discussions that went on forever, and the mathematics that they were talking about could have really been handled in about 5 minutes, because it really wasn't challenging enough to warrant the kind of time spent. So when I talk about this, saying you want to identify a task that's aligned with the goals, certainly that. Making sure it's rich enough to support a discussion. If it isn't, then don't have a discussion or pick another task. So I just want to say a little bit about the task thing. I've given you some handouts, primarily because I wasn't sure who was going to be here in terms of math or science or people's level of familiarity or expertise. So you have a purple sheet that has the task analysis guide on it. And that's basically a tool that we have been working on for probably 20 years, where we try to identify the characteristics of tasks that we consider high level and low level. And the characteristics on the right are associated with high level tasks, and the ones on the left with low level. And then I've simply given you 2 examples of tasks that fall into different categories. So on the solving systems of equation, and some of you saw me talk about this yesterday, task A would be a doing mathematics task, and task B would be a procedures without connections. On the back side of that, version 1 would be procedures without connection, and version 2 would be doing mathematics. So my intent here is simply to provide an exemplar of what I mean by high level in case that language is new to you. I know the Georgia students are probably better versed on the particulars of some of that than I am, or so it seemed yesterday. Regarding the science, again, so I will make the disclaimer that I'm a little bit out of my element here, but the green sheets will give you some information about how we have talked about tasks in science. And the first green sheet has along the side 3 different kinds of tasks: explanation, data representation, analysis, and experimentation. And what we concluded with a lot of help from Jen Cartier is that there's lots of different kinds of things one does in science because of the nature of science. So rather than thinking about tasks in general, we've chosen to talk about tasks in these 3 categories. So, because sometimes students are asked to provide explanations, sometimes they're asked to represent data, and sometimes to actually design protocols and conduct experiments. And sometimes they do all of those around one particular topic, and sometimes they just do pieces of them. So what this table is trying to lay out is what might be low and high level related to each of those categories of tasks. And then on the subsequent pages, and these examples come right from the 5 Practices in Science book, there's some examples of what we would consider experimentation, data representation, and explanation in each of the high and low categories. Okay. So I'm not going to say any more about it, but that'll give you a sense of at least where we're coming from. Okay, so anticipating is about the array of strategies that students might use. That's what I said when I started this. It's a little bit different in science, I've come to believe. So it's not so much about strategies. It's often about features that must be present for complete and correct design, explanation, or representation. So, for example, when I think about something like proportional reasoning, I can imagine that you could solve a problem using scale factor, you could scale up, You could use unit rate, you could use cross multiplication. You might cross that with some representations. You could draw pictures, you could make a table. So there are lots of different things that you might do in terms of strategies and in terms of representations. In science, it's not so much that there are wildly different strategies, but there may end up being, you may use different representations, and that might not be the feature that's really important. It's about what are the features of the representation that we wanted to make sure you captured. What are the components of an explanation that needed to be there for it to be complete and correct? And I'll give you an example of that in a second. So it's supported by doing the task in different ways. So you should have some sense of what people are likely to do. And part of that comes from having done it yourself. We were talking about this in a couple of meetings I've had over the last 2 days. And one of the things I hear a lot is, I only know how to do it one way. Well, then start getting creative about how you're going to get some input before you go in and teach a task that you can only do one way. Because I can't imagine anything scarier than a task that's really open-ended and giving it to students and only knowing one way to do it. What are you going to do with everything else that happens? 2 weeks ago, I was doing some work in Colorado, and I met a young woman who was in her second year of teaching, and we were talking about, I wasn't talking about the 5 practices, but she asked me about the 5 practices, and she said that she found anticipating to be particularly difficult to do because she didn't think she knew much. And so what she had started to do was she was using social media to help her, and she was literally posting a task on Facebook and asking her friends to weigh in on how they would have solved the task. And one of the things that she found, I'd actually suggested this to some of my students and they thought I was nuts. And one of the things she found was people actually responded to her, and that non-math teacher people actually had more varied responses, more intuitive responses, and in some ways responses that were closer to what her students actually ended up doing. And so she found that to be a fairly productive way to expand her repertoire of what kids might do. And I thought, it's perfect. Now and also, I mean, those of you who are in teacher education programs, I mean, the people sitting next to you should be really good resources. Even in my group of 7 that I worked with on Wednesday, individually they were able to come up with 2 different things on the solving systems of equation task. But by the time we put it all together, we had like 12 different things that students might do, and they were amazed. And that wasn't really even going outside, tapping knowledge outside the group. So discussing the task with other teachers seems important, and that doesn't have to be face-to-face. That's my point here. Drawing on relevant research and documenting student work from year to year. If you use a task once, collecting the student work, and by collecting I mean in this day and age, walking around with your camera and photographing unique solutions to a task and then storing them in a way you can actually refer back to them. I mean, back in the day, I remember, this is dating myself, but that probably is obvious anyway, transparencies with solutions in multiple color markers and putting them in plastic sleeves, and then after a few years, you know, the whole thing is like one bleeded together mess. Technology has really helped us make progress. Some teachers have been telling me how they've used the iPad to actually do this, and that, especially the newer ones, have pretty good cameras on them. And then they can actually include notes from the class along with the actual photographs, which I thought was a really, really good idea. So monitoring, as I said, this is about circulating around the room, seeing what people are doing, asking them questions, but it's not on this list, but I would want to add, not hovering too much. Yesterday someone asked me, you know, if you have 8 groups, how do you get to everyone? And I said, well, you can't stay with any one group until they finish the problem. So you have to make sure that you're giving them enough to make progress without waiting for it all to be resolved. because that also sends the message to students that they're capable of making progress without you. And what you're going to see here is every practice is supported by the practices that came before it. So I just want to give you an example of a monitoring sheet in each discipline. So this is a sheet. The problem that I was talking about here is the leaves and caterpillar problem, which basically caterpillars, there's a certain number of leaves that 2 caterpillars eat 12 leaves. I can't remember the exact problem. And you want to know how many leaves you need for some other number of caterpillars. I thought I had written the problem down, and it turns out I didn't. Anyway, it's in the introduction of the 5 Practices book. But the strategies that I thought people would use to solve it would be unit rate, scale factor, scaling up, additive, and at the bottom you can't see it, but some students actually multiplied the leaves and caterpillars together. Now that wasn't something that we anticipated, but it was something that we actually saw students do when we walked around the room. So armed with this, now we can actually see what actually happened. So in this particular case, what happened was we made note of who used particular strategies and also what representations they used. And then in the last column, which I'll get to in a minute, we talk about which of those would be the ones I would want to have shared publicly based on what I'm trying to accomplish mathematically. So that what happens is, I'm going to argue the monitoring sheet serves several purposes. One is, the immediate purpose is, you've got a lot of data here on which to draw and making decisions about what's going to come next in the class. Beyond that, you've got some data about where your students are. So from this I know Janine's using a unit rate and she's drawing a picture. And Kyra's was just a picture with no number sentence. So that tells me something about Kyra. She was able to solve the problem. She's using a pretty primitive strategy. So I'm probably going to be wanting to keep an eye on Kyra so that the next time when I up the numbers that we're using, and now you're trying to find it for 100 caterpillars or 200 or 1,000, I want to make sure she's not drawing pictures anymore. So this actually allows you to sort of see where students are and to track that over time. Now, as I mentioned before, in science, it might be a little bit different. This is a task that we talk about in the book that we call explaining the behavior of water. And basically, the students have done various experiments. Whatever. Students do various experiments with water as a liquid, solid, and gas. And they're supposed to be, through these experiments, coming to some conclusions about how water behaves. And now, when they move to this task, they're trying to explain at the molecular level what's happening there. So what the teacher's done in this monitoring sheet is she's indicating what are the features of an explanation that you would need to see. You want to see that the spacing of the molecules is correct, so that they understand that molecules are more tightly packed in the liquid rather than in the solid, which is unlike other substances. That heat is what's necessary to move from one state to another, that molecules are moving, and that in the solid form they have a crystalline structure, that there's forces that are keeping them together, that they're the same size and type molecules. So these are the things. So it's not so much that there's a different strategy, but it's like, what are the elements of the explanation do I want to be looking for? And then over here, what things did they get right and not? So at the end of the day, this is just what was collected from 3 groups. You can see exactly what features they correctly represented, what they incorrectly represented, and then some additional notes from the teacher. So what the teacher then has is, okay, so the only thing this group had correct was this. But that's a point I want to make, so maybe I'm going to start there in terms of having that group present. There's a very detailed case about this particular task in the new book, if this is something that's interesting to you. Okay, I'm keeping an eye on the time. I'm notorious for having more than one could possibly do in the amount of time I've allocated. So selecting is probably pretty straightforward. Which students are you going to call on to put their work up? And because in most classes you don't have an unlimited amount of time to spend on this, I think you need to be very strategic about how many solutions and which solutions are going to best help you make the point of the lesson. But also trying to balance making sure that you call on students who need an opportunity to show their competence, that you're not calling on the same people all the time. So one of the things that you might notice in some of the monitoring lists is that sometimes there's multiple people who do the same thing. So you might look and say, okay, 3 people did this, and this person hasn't presented in several days, so I'm going to call on them. So that you can still make decisions that have to do with equity. And as long as students understand how such decisions get made, and over time everyone gets an opportunity, I don't think that students end up feeling like their work isn't honored. You can spend a lot of time having every group present, and I've seen this happen in classrooms, and after the 3rd or 4th person has presented the same thing, everybody's eyes are glazing over. I'm also a big fan of having control over the content that gets presented. As soon as you say, who wants to go next, some of the most dangerous language you can use in a classroom from my perspective, you are turning your classroom over to a teenager because you don't know what they're going to do. And what they're going to do might be perfectly aligned with what you have in mind and where you're going. But 9 times out of 10 it doesn't. And sometimes, I actually have had this happen where the person who volunteers to go first does the most sophisticated, most advanced strategy, and everyone else is like, huh? So trying to think about both the selecting and then I'm sort of talking about sequencing at the same time in a way that makes sense. And again, the practices that came before it help you do that better. Sequencing, I just talked about that. Purposely ordering the presentations. Sometimes that might be going from least sophisticated to most sophisticated. Sometimes it might be starting with the misconception so that you can get that out on the table. It might be going from concrete to abstract. It could be going from the most common, the most popular, to something else. So it's not a one-size-fits-all strategy here. It's about thinking about what makes sense in the context, but having some purpose for doing it in a particular way. Sometimes you might pick this one and then that one because somehow putting those next to each other really allows for kind of analysis that it would be hard to do if they weren't juxtaposed. And connecting is basically encouraging students to make connections between different strategies and making sure that the ideas that are at the heart of the lesson are coming out. That's really the key here. And it's supported by doing all the practices that came before it. So yesterday, one of the pre-service teachers asked me, you know, if there was like a practice that we could focus on first, what would be a good first practice to work on? And the first practice. But I would actually say a really great starting point are 0 and 1. So setting a goal, selecting a task, and anticipating. Because I think if you actually spend a lot of time focusing on those, you get a lot of the rest of it. Because when you started monitoring, even if you weren't keeping track of it all, even if you weren't consciously monitoring, because you had anticipated, you're so far ahead of the game in terms of your ability to notice what was happening in the classroom. So why are these practices likely to help? Well, as I said, I think they provide teachers with more control over the content and over teaching moves. Not everything is improvisational. There's still going to be some things you hadn't anticipated, and my view is by having anticipated this much, when you get to this piece that you didn't anticipate, you at least have the cognitive space and energy to be able to try to think about that. It provides teachers with more time to diagnose student thinking. So when somebody's doing something that you hadn't anticipated, really trying to get at the root cause of that. To plan questions and other instructional moves. It provides a reliable process for teachers to gradually improve their lessons over time. So you teach a lesson, it's important to reflect on it, collect the data, and when you go to teach that lesson, or even any subsequent lesson, you think back on the previously taught lesson. And this is probably among the most important. It honors students' thinking while guiding it in a productive disciplinary direction. This builds very closely to the work, Randy Engel's work on productive disciplinary engagement. And so the key is to support students' disciplinary authority while simultaneously holding them accountable to the discipline. But the guidance is done mostly under the radar. So what I mean by that is, as an instructor, I've made most of the choices, but the work that's being featured, the things we're talking about, are actually the things that students have done. So while I'm in control, always, it's really under the radar. And a lot of times, students don't even realize that you actually did a lot, even though it appears you did nothing. At the same time, students are led to identify problems with their approaches, better understanding sophisticated ones, and so on, and it fosters students' accountability to the discipline. Oh, that's the same thing over again. I thought I took those slides out. It's the problem with Dropbox. I hadn't updated. So let me just tell you a little bit about what we've been doing. So our earliest efforts showed that pre-service mathematics teachers could identify 4 of the 5 practices when they were embedded in various teaching contexts. And some of the pre-service teachers really had started to learn how to apply them in pedagogical situations. Now, you can imagine what the 4 of the 5 might have been. You can't really observe somebody having anticipated. You can imagine that they must have. But this ends up being pretty important because they really could pick up on, even when the practices weren't named, when a set of practices were repeatedly done, they began to be able to identify them, call them something, and recognize how that practice was helpful. So what we really wanted to do then is we wanted to determine the extent to which teachers could actually enact the practices in their classrooms. And we also really wondered whether using the practices supported implementation of tasks at a high level, because remember, that was really the whole point. So we engaged in a full year study of this with some practicing teachers in a local school, and we learned a lot, although it wasn't necessarily what we might have hoped to learn. So one of the things that we learned was anticipation is really the cornerstone, along with the goal setting, I might add, on which the other practices are built. If teachers do not engage in anticipation, they don't engage in the subsequent practices in more than a superficial way. So what we had created is a tool that we call the look-fors, and is a very detailed protocol for classroom observations that allowed us to look for teachers doing certain things. And you can find evidence of them doing some of the later practices, but they weren't done in a very meaningful way that led to the kind of outcome we were looking for if they hadn't anticipated. And the fact of the matter, the teachers with whom we worked did not engage in anticipation individually, even though that was part of, we met with them every week for a school year, and their job was to use this particular tool and put in their anticipations, and virtually nobody did. The only time they anticipated was when we met together as a group and did group anticipations. And then, depending upon the extent to which they looked at the task in advance, those ended up being very fruitful opportunities. And what the teachers, and we have some evidence that suggests that when teachers had really specific learning goals and engaged in these group anticipations, they were better prepared to enact tasks at a high level. But it seems to be, and we're still trying to sort of tease out some of the things that were going on there, but without anticipation, it seems that teachers are not equipped to actually make the kind of progress you would hope. And that kind of makes sense when you think about it, because anticipation is what allows you to have the eyes to see and to listen to the student thinking. So what we're doing right now is we've backed up and we're actually looking both in math and science at how teachers learn to anticipate, and we're studying the lesson plans they produce in both disciplines over the course of the year to see if we see increased ability to anticipate what they're actually doing. And we may end up looking at some of the classrooms in the spring. We haven't decided on that yet. So I will stop there, 5 minutes beyond when I was supposed to, and give you an opportunity to ask questions. That's where you can reach me if you have any questions you want to ask on a one-on-one, and that's where you can find the science educator. So questions?
Does anyone have any questions?
Yes.
So with your 5 practices, have you seen any correlation or any type of relationship between the practicing teachers or in-service teachers' sort of pedagogical orientation, such as like a culturally relevant pedagogy, or if they have a sort of social justice pedagogy towards their use, or how they use the 5 practices thereafter? Or even in the sense of beliefs about mathematics and teaching, have there been a correlation on how they use them?
Well, definitely. I mean, so that ends up being, and so first, in terms of the social justice, culturally relevant, I don't think that what we're suggesting here needs to be inconsistent with that. And in the school that we worked for 4 years, they also were doing professional development related to culturally relevant pedagogy. And what we tried to do is talk about how the things we're advocating were in the same space as what they were learning in this other more generic sort of professional development. But certainly what happens is, I mean, you can imagine, and this happened with the science teacher that we studied very carefully. She was a second-year teacher, and she was very gung-ho, and she really wanted to do this, but the tasks that were in her curriculum were really not good. And what we found is it's much harder to take a task in a science textbook and turn it into a good task than it is to do that with some math tasks. So she ended up thinking she was doing the 5 practices, when in fact it was, she was doing the 5 practices around pretty procedural problems. In her case, and she was not completely aware, without some guided reflection, that that's what she was doing. So we also have worked with a number of teachers in that same school who didn't want to buy what we were selling. So it's the same sort of thing. I'll do the 5 practices, but I'll do them with my tasks. So some of the pushback is about my kids wouldn't learn this way, or, and I'm using quotes because this is not my language, I have the low kids, and they can't do the kind of tasks you're talking about. So you get a lot of pushback. This was also a school where there were, it was one of the most impoverished neighborhoods in Pittsburgh, and there were a lot of struggling students. So we got a lot of that. Oh, yes?
Okay, yeah. Can I follow on directly from what you just said? Because looking at these 5 practices, you said that they did for their types of tasks, right? I think that's what I heard.
Mm-hmm.
Is there anything in here and I look at them, it seems like I could do these five practices with entirely procedural learning, for instance. Am I correct? Or, in other words, is choosing the task separate from the steps involved or not?
Well, but remember, the bedrock practice here is setting a goal and selecting a task. So yes, you could do these practices with any task, but if your goal is to engage students in high levels of thinking and reasoning, and if your goal is to build on student thinking, then you have to have a task that actually provides an opportunity for students to think. So if you look at, I would argue that when you look at the math examples I gave you, tasks A and B on solving systems of equations, task B is a very procedural task. Now, you can do the 5 practices, but okay, I just taught them how to solve systems using elimination and substitution. So I'm going to show each one of those, which of course we've already done because that was part of the instruction. So there's not much, and there's no explanation required in the task. There's no opportunity really, I mean, what students are likely to do is very bounded by the instruction that they just received on how to do it. So yeah, you could do the 5 practices, but the whole intent is gone because of the nature of the task that you've selected. Now that's not to say, I mean, if you're going to use a procedural task, there's some benefit in trying to think about how students are going to incorrectly apply the procedure so that you can diagnose them. But it's very different than thinking about, I mean, again, if you go back to one of the early slides where I said the purpose of this model was to help teachers moderate the amount of improvisation needed in a student-centered lesson. So that's really the key for me.
Any other questions?
Yes. Right here.
Like you just said about the student-centered tasks, how do you change your classroom from a culture of students that are used to the lower level, cognitive questions, to a classroom that discusses and talks about what they learned instead of just listening to the teacher?
Great question. My first answer is not overnight. Slowly. So it's more difficult to do it, I think, the higher the grade level. What grade do you teach?
It will be high school.
Okay. So somebody yesterday said, I teach 11th grade and they're pretty used to doing things in a particular way. What are you going to do? And it's like, well, I think what you have to do is you start slowly. And you start with maybe a more bounded task, like a procedures with connections sort of task that provides some direction on what you're supposed to do. But the high-level part of that is trying to look at what you've done and then trying to make sense of it or explain it in some way. So I would be really thinking about the nature of the task. Also, I was telling a group yesterday, if you could find a really motivating task, one that students might actually get excited about doing, you may find that a good entry point. I won't go into the details, but Bungee Barbie is probably, in Western Pennsylvania, Bungee Barbie is really popular. And I have seen, 12th grade male students who most days have their heads on their desk, out in the hall, dropping Barbie over the banister with rubber bands attached to her foot and measuring how far she is from the ground, okay? So now, you might be saying, where's the mathematics there? Actually, there's quite a lot of it. So I think if I were doing something for the first time, I might really try to change it up into the kind of activity that they wouldn't expect to see in a math class. Now, you can't be throwing Barbies around every day, but there are things like that. And I've actually seen that task done in the middle school. I've seen it done with 11th and 12th graders, and I've never seen a group of students that didn't get engaged with Barbie. And you might even think that 11th grade males would go, Barbie dolls? You gotta be kidding me. But no, it's like, give me that Barbie and let me see how far I can throw her over the banister. I mean, it's really quite a phenomenon. So I think a lot of it has to do with finding tasks, too, that might be motivating. and not expecting it all to change overnight. And not giving up too quickly.
Yes. Any other questions? All right, thanks so much. Oh, yep, go ahead.
Just one, I'll do the final one.
Okay, you can have a fun questionnaire.
So my teacher liked to do, I think, a superficial 5 practices in high school, and she loved to call on students with incorrect solutions as a teachable moment. Do you think that's compatible with the 5 practices?
Oh, absolutely. In fact, I mean, that's one of the strategies we talk about. So, but I would be very targeted about incorrect answers, because there's a lot of things kids do that are incorrect that may not be worth discussing or making public. You know, if I added wrong, if I, didn't put a placeholder when I multiplied, I'm not sure that warrants class time. But like in the problem I was talking about, the leaves and caterpillars, if I added instead of multiplied, that would be something that's probably worth discussing, because it is the biggest misconception in the domain. So getting that out publicly and inviting all the students to try to figure out, why doesn't this work? What's going on here? Seems like a really important opportunity. But in order to do that, I think you needed to have created a classroom environment where students really feel like being wrong does not mean I'm stupid, wrong answers are an opportunity for new learning, or whatever the mantra is. They have to feel like there is, this isn't a judgment. But absolutely, I think to ignore wrong answers, sometimes I get pushed back that, well, I don't want to put anything up that's wrong because maybe they'll remember it. And my comeback is, like, they remember everything that's right that we put up? And with that, I'll say thank you.
Thank you.